Hello, everyone. Welcome to MLAS 500. This is our inaugural lecture for the fall of 2026. This is for Reinforcement Learning and Autonomous Systems, course number 17706. 3 credit hours, and it's a course date that starts August 24th and ends December 11th. It's a hybrid class. We have online students as well as in-person students. The way we're going to be set up is weekly meeting times Tuesday and Thursday. Our Tuesday meetings are going to be via a Teams meeting that will be available for our students. For our both in person and as well as our online students. Tuesday we will meet regardless of whether you're in person or online. Tuesdays will be a Teams meeting at 1:05, and I'll get that set up and sent out for everyone. And then Thursday, we will have a in-person. It will be in person and recorded as well for the online students. So the online students don't have to come into class on Thursday, but we have an in-person lab on Thursday that's recorded. And then for the in-person students, we'll run that lab just live in the course room, in our classroom. Sorry. So prerequisites for the class is Stat 225 and MLAS 350. And so my contact information, if you have any questions, you can shoot me a text message via my phone, or you can shoot me an email at mjp001@ksu.edu. My office hours, I'm here on campus, but I'm also available via Zoom or Teams. If you give me a heads up, I can, we can schedule out a Teams meeting and we can schedule virtual office hours that way. I'm also available here in my office if you want to meet for the in-person students. That's also available. Our class resources will be using Google Colab, Python, NumPy, MATLAB, PyTorch, Gymnasium, as well as TensorBoard. That'll be the computer environment. So if you're not familiar, it's essentially an online Jupyter Notebook framework. It works really great for a lot of different classes. But especially the lab portion of our class. We'll probably take a stab at stable baselines as well. But that's our computer environment. We don't need anything special or anything. You don't need to download Spider or VS Code or anything like that. We'll just be using Google Colab for all of our coding for the lab portion. So you do have to have some familiarity with Python. You don't have to be an expert. But at this point in time, you should have some intermediate capability around Python and have familiarity with that. Again, you don't have to be an expert. We'll run our labs live and then and all done via Python and the Python libraries for that support machine learning frameworks, especially around reinforcement learning. There are no books that are required for this course. We'll be using essentially everything out of the box from a Google Colab and Scikit, as well as all the extended libraries we need. If there are any course materials, any reference materials, I'll provide them, and so there's nothing you have to go out and purchase. From a course perspective, the course description, we'll be going over Markov processes, Q-learning, artificial neural networks, recurrent neural networks. We'll get into generative adversarial networks to a certain extent as well. Those all reinforcement learning forms the basis of all of those type of algorithms and those RL networks, as well as the more advanced deep learning networks that are OpenAI and the large language models you see in Gemini and large language models that are Anthropic. They all are based off of some form of reinforcement learning. So the course from a high level, we'll get into a lot of the stuff that just builds upon from what you learned in MLAS 100, what you learned in MLAS 200, and then what you're going to be learning in unsupervised and supervised learning in addition to reinforcement learning. All of those are ones that they all build upon each other. And so one of the things that I'm expecting out of this class, and what I hope you learn is your ability to be able to explain the different algorithms that we're going to be using within the reinforcement learning, computational learning theory, what the subcomponent of reinforcement learning within computational learning pieces, right? Whether it's supervised learning, unsupervised learning, or reinforcement learning. We're focused on reinforcement, and so I'm hoping that what you get out of this is being able to have a better appreciation for the reinforcement learning algorithms, but also implementation. Not just the foundational stuff, but being able to like take what we learn from a theoretical perspective and actually put it into practice through code. That's where Google, the Colab environment is really useful. But also analyzing what reinforcement looks like, just exploring different strategies, performance measures, being able to kind of tweak the code and go, oh, okay, if I tweak this, then this changes, right? It's kind of like I like to use the Marvel Cinematic Universe, the Marvel like kind of superpowers as an example, right? If you pick up a power, a new power, or a new capability, there's usually always a trade-off with that new capability. And so I think that's really important to kind of understand, like, if I go this route, then what's the trade-off for that, right? I make it better doing this, but then there's always a cost to it. And so we'll be exploring that, and then design functions, architectural, system level type of views of what we're building as well from an applications perspective is something that I'd be expecting you to have, as well as being able to evaluate the outcome, communicate the performance limitations, be able to communicate like at a high level what is it that we're building. Okay, so grading policy straightforward. Grading 90 to 100 is an A, 80 to 89 is a B, 70 to 79 is a C, and then of course below that is pretty self-explanatory. Attendance policy. Regular attendance, you want to make sure that you're checking in with the classes, that you're checking online for the online students regularly. That you're attending the labs, you're attending the the Teams calls. And if you do that, you're going to be okay. But I understand that stuff happens. So if you miss one or you miss something, it's not going to be the end of the world. You've got a job, something happens. You got a family event, something happens. That's okay. But the courses and the modules do build on each other. So you want to make sure you're just staying on top of the class weekly, and you'll be fine. But if you fall behind and miss a class here and there, or you miss a lab here and there, it's okay. All the material is going to be made in Canvas. It's going to be, all the modules will be made available, and they stay available for you throughout the course all the way up to the last day. With that said, you don't want to be caught at the last minute, within the last week, or the last couple of weeks, like trying to scramble and get everything done. That's just not, you won't have quality work, you won't have quality output, and it's of course going to impact your grade and how well you do in the course. So keep that in mind. So course modules, the module, I'm not going to read all of these, but make sure you kind of give this a good read, look over all the different things we're going to cover. We're going to go through foundations, Markov decision process. We're going to be doing some dynamic programming. There won't be it's not a math class, but we will have some occasional math that pops up. But we're not going to be like, quizzing on math and things like that. But you need to be familiar with where the basis of reinforcement learning comes from, and where it's at right now, and how to use it, right? How to program in it. So then we'll have Monte Carlo type things. We'll go through Q-learning, deep reinforcement learning, and then we'll get into actor-centric methods, as well as reward engineering, and how that impacts navigation robotics and sensor simulation, autonomous decision making. Now, we won't be working a lot with hardware like you did in MLAS 200. Almost everything we're going to do is going to be programmed, and then we'll discuss how that programming and the embodiment of that programming can show up in robotic systems. So we will cover some of that. But we're going to be heavy in learning, reinforcement learning, and programming. So the grading rubric is pretty straightforward. We've got 4 quizzes. There's a quiz 1 that goes through modules 1 through 3, quiz 2 modules 4 through 6, and then quiz 3, quiz 4. We do have assignments. These are programming type assignments that are also part of this, like implementing a basic reinforcement learning model. So you'll have 4 of those assignments, 3 assignments, and then a final exam. The final exam is going to cover everything: concepts, reasoning, code interpretations. It's going to be all modules, all topics. But what I do that's a little different is the quizzes are going to be unlimited retakes. You can take them as many times as you want, and so that I feel that's important. The final exam, you will be able to take up to 3 times. So in other words, if you don't like your first one, you can try it again and go through and try to get a better score. The assignments are going to be are like Jupyter Notebook kind of assignments. So that's where that comes from. So there'll be a coding assignment, and you'll want to code out as an example, implement a basic reinforcement learning model. You'll have some code, and then some code will be taken away, and then you have to essentially like build it out and make sense of it. So okay, so we will put a pin in all, or not pin, but finish that up for the grading rubric and the final exam. Let's see. All assignments will be on Canvas. This goes for both in-person and online students. All of it will be managed in Canvas. So assignments you'll submit your assignments in Canvas, and the quizzes will be in Canvas as well. Okay, for communication, if there's anything, if you want to meet with me, or if you have anything that pops up, just text me or email me. If you want, if you are interested in like virtual office hours, just give me a time and we'll get it on the calendar. It's pretty straightforward. Later missing work, I leave all the assignments open and available to the last minute, to the last day of class. Now, like I'd said earlier, you don't want to get into a situation where you're scrambling at the last minute, because that's just you want to just stay on top of it weekly. But again, do understand if something pops up, you can make work up all the way to the last minute. So if you have something where it's like, I got to this assignment, but I missed this quiz, you can take the quiz. It'll stay open. But if you have an assignment that you missed and you need to circle back on it, you can do that too. Now, with that said, I highly encourage you to stick with the course and weekly. And if you do that, then assignments and anything that pops up, you'll be okay. Okay. Let's see. I should be able to get, like, from expectation from me, I will be able to get usually within 5 days of assignments that are due. I'll have them graded within the week. And then, of course, if I miss something, it can happen. Then just shoot me again, text or email, and I'll get that taken care of. I would, because this is reinforcements, 500 level class, I'd expect to be spending 8 to 10 hours a week in the class, like outside of class, studying the material and learning the material. And so you'll want to make sure that you budget that appropriately in terms of how much time I would expect if you were taking the class. So okay, let's see. And I think the rest of this stuff is fairly boilerplate: electronic communication, technology requirements. If you have any technical difficulties, make sure you reach out to helpdesk@kstate.edu. Make sure all the work that you do is yours. I don't mind, and because we're teaching an AI course, I don't mind that we're going to be using an AI on occasion to help us build some of this stuff. But I do expect that you understand the code that is underlying what we're building. And also one more note on the quizzes and also the final exam, it's open book. It's open notes, open books for any and all of the materials, so you can use that and to take the quizzes. So that's just to circle back on that piece of it. That's totally available for everyone. Let's see, expectations. Yeah, just, I think the big thing is if there's, just be cordial when you're talking to other students, and understand where everyone else is coming from. And I think a certain amount of, I just don't want this to be if there's any that everything is communication is open and accessible, and we aren't getting too worked up about that. We're making sure that we're using respect when we're talking to each other. So, okay. Let's see. Statement on mental health. If you have anything, we have resources that are available at kstate.edu counseling, as well as the Lafine Clinic. And then if you've got any campus safety concerns or anything like that, definitely feel free to I guess just reach out to campus police, or if there's any type of things like that and that pop up. Okay, so I think that's all I've got for this. And now I'm going to switch over to a presentation for talking through just the refresher. Okay, so this is a reinforcement learning. This is kind of our first lecture, and this is a refresher is where I'm going, just a machine learning refresher. You've seen these slides before. I actually gave a lecture on this in MLAS 100 when you were doing a survey of machine learning. So we'll cover this again because it's definitely important. It gives you a high level of what we're working with, and then there is also, I'll run through this real quick, but then also go through and talk through some of the other. So this is kind of actually going to be two lectures. Okay, so all right. So machine learning, we've got supervised, unsupervised, and reinforcement. That's kind of your big thing. You've got clustering for unsupervised, regression classification for supervised, and then reinforcement learning gets into something a little different, right? It's one of those areas that, when you talk about reinforcement learning, it's based on a reward system, right? Agent and reward. And that makes it a little different. The other piece that I want to talk through is that when we think through supervised learning, unsupervised learning, a lot of that world is based on Bayesian conditional probabilities that happen in the past, or events that happen in the past have probabilities that can be assigned to them. And those probabilities have an influence on future probabilities for future events, right? Now, reinforcement learning is a memoryless system. In other words, it's not bound by prior probabilities or prior event probabilities. It's a current state probability, and how that works in the present, with the added wrinkle of a reinforcement, with a negative or positive reinforcement loop added to it, to influence the probability and of what can happen. So that's kind of the high level. Supervised learning, you've got for classification, you've got it's similar to unsupervised in that classification. The big difference between supervised and unsupervised is that supervised learning uses training data, labeled data, whereas unsupervised uses non-labeled data. So in supervised, we use classification, and then regression we use for prediction. Now, in unsupervised, we use dimensionality reduction to reduce, and it's good for a lot of different things, but we cluster data sets. There's a difference between clustering and classification. Classification is a classification is labeled, trained data that is used for categorizing data points. Whereas if I want to categorize data in unsupervised learning, it's called clustering, and it does not use labeled data. So clustering does not use labeled data. So that's the distinction between clustering in unsupervised and classification in supervised learning. Okay, reinforcement learning. This is an MDP, Markov decision process, and we talked a little bit about this in class, but I wanted to bring this up in that it uses a reward system, right? So I can get these feedback loops that are in this current state that influence negatively or positively my state. So if you think about like reinforcement learning from, like, let's say if I'm a robot on an industrial robot working on a line, I have a start process. Let's say I work on doors, and then I pick a door up, I weld the weld points, and when I pick that door up and then I put it down for another robot to pick up, right? That's the end of my state. And then how well if I weld really well my weld points on the door, right, then that's positively reinforced, and then I will do it better next time, right? I'll be more precise, right? And that's kind of like a really clean cut example of reinforcement learning. Now, reinforcement learning in the case of like something we're looking at here is a little more complicated. If it's a person going through their day, right, they get up, they go to work, if I got coffee in me, does that positively reinforce or does that negatively reinforce, right? Or if I take too much coffee, right, does that overly negative reinforce what's going to happen in my day, right? If I get in an accident, if I call in sick or whatever, right? That totally can have an impact on me getting home later in the day. And let's say I get home late because of all the things that happen or the distractions, right? That's a very real possibility. And so it gets kind of fuzzy, right? Because it's subjective too, because what's to say that somebody doesn't have coffee and that's actually a positive reinforcer for that person, right? So it's relative. So each system has to be taken into context for reinforcement learning to have an effect that can be measurable from a probabilistic perspective. And there's a lot of context to it, right? Again, each system is different, and each person moving through their system is different. Okay, so that's just a quick high level on reinforcement learning. So I wanted to show this off, scikit-learn Python library. We're going to be using this quite a bit. There's a lot of good stuff in here. And then here's a cheat sheet for algorithmic speciation. Again, this is just classification, clustering, dimensionality reduction. This isn't anything that we made here. This is all something from the scikit-learn website, but it's a good visual, kind of give you a high-level idea of kind of what we're working with from an algorithms perspective. That differentiates us from, let's say, classification, regression, clustering, dimensionality reduction. And these are all their own different types of algorithms, the things that are in the square, like randomized PCA or kernel approximation k-means for clustering. Those are all different algorithms for different outcomes, right? Like regression is supervised, classification supervised, clustering and dimensionality reduction. Dimensionality reduction is unsupervised, clustering unsupervised. These are more of This just kind of give you a high level of where the algorithms fit within their specific use cases. And we have one that we're going to create that's different from this, that's for reinforcement learning. Okay, so that's all we have for this refresher on this one. And I've got one more that I want to cover, and it's just, now that we went high level, let's talk through just a couple examples, right? So computational learning theory is everything we just talked about: supervised, unsupervised, reinforcement, and deep learning. Deep learning is one of those newer areas. I say newer, it's been around for now probably 10, 15 years now, but it's highly dependent on reinforcement learning. So deep learning is what we talk about when we're talking about neural networks, large language models, multimodal models, those frontier models that you hear about: Anthropic, Gemini, OpenAI. And but for now, what we're going to do is we're going to run through some examples of what that looks like. So for unsupervised learning, we take input data, we have a model, and we cluster the data. So, but the key distinction here is the input data does not it's not labeled. We don't use training data. We just take the data, and then we vectorize it. And in other words, we create a numerical value for it. So apple could be 0, peaches could be 1, bananas could be 2, right? We assign a numerical value to that. Now then, because we do that, we can actually cluster to the data. We can say, oh, these apples approximate 0, so they cluster around this axis of 0. Same for peaches, same for bananas. Now, again, the difference is clustered data does not have labeled data. And so what that shows up in terms of, like, so if I have an example of a text string, and in this case, BOX, and now in this text string, it's just the text is all over the place, but I can assign I can take the token, in this case the letter, and then I can vectorize it and give it a numerical value, and then I take that numerical value and I can get a pattern off of that. And so I can ask the question, what is the pattern? And I think that's the big thing for unsupervised learning. What is the current? Just describe what I'm seeing. That's all clustering is doing. And that's a distinction from what we're going to see next, which is supervised learning. I can take the same data, but then I can ask an extra question. Not only what do I see, but what's going to grow best next season, as an example, or what will happen next is really kind of what I'm asking. So in this particular case, supervised data is labeled data, right? I have labeled data, I have training data, and I can do interesting things with it once I do that. So I can take them, I can take apples, I can take peaches, and I can take bananas, and I can ask the question, okay, what's the current state of what I'm looking at? Describe what I'm looking at. But I can also now say, well, predict what's going to happen next. You might be asking, like, well, how do I do that? So let's take our string example. You take the data, I have a string, and I have the same thing, but I apply an algorithm to it that's a non-descriptive algorithm. In other words, I just don't tell me what's going on. Just don't give me a count and then go, oh, let me cluster where these things are at. But let's apply an average to it. But let's make the average moving. So then when I do a moving forecast, when I do a moving average, or apply an algorithm, it's a moving average algorithm, then I can actually I can ask what happens next in the sequence. I can forecast what's going to happen next, which is kind of cool. Well, in the data, this is how that would look. I have a moving average that moves from the training data through to the prediction, and it gives me a prediction of what I'm going to see next based on what I see in green, which is the training data, versus blue, which is the prediction, which is very different from unsupervised. Unsupervised can only look at the data that I have and then show me what's going on, because it can't go beyond that. Now, I don't want to split hairs. There are situations where it can go beyond that. But for us and what we're doing right now, this is where you need to be. Okay, so reinforcement learning is different from the other two, both supervised and unsupervised, in that I have a reward and an agent for that reward. An agent lives within an environment, and that agent behaves according to rewards that are impressed upon it. So in other words, it could be negatively rewarded or negatively reinforced or positively reinforced. So using our same example with our string example, I can now layer in another layer. I can now add in and say, don't just show me what's going on and don't just predict what's going to happen next, but I can actually positively reinforce or negatively reinforce the future behavior of that prediction, and then tell me what's going to happen next. So it's a different way of thinking about it, and the way I can do that is taking the same data, right? I can add in ones or negative ones. I can add in another line that adds in an extra level of reinforcement to the moving average so that I can affect, or the environment, let's be clear, it doesn't necessarily have to be a person, but that makes the adjustments to this environment, but that stressors within that environment can negatively or positively reinforce or not reinforce any decision outcome that occurs as the person and or agent is moving throughout the system. And so this is how that can happen, right? As an example, I can be positively reinforced this morning by having a good cup of coffee that I absolutely enjoy, and that positively influences my day. Now, versus I get into a car accident, that negatively influences my day, right? And so that's a high level. So the green that you see here could be my coffee, and the -1 in red could be the car accident. And mathematically, this is how, keeping all things equal, if we create an extra line here that captures that data point, then I have a reinforcement learning model. And then I can now do a lot of cool things by overlaying this extra data onto it, because I'm capturing now another layer that I wasn't in the previous two steps, right? Okay. So with that being said, that leads into deep learning. Reinforcement learning models and neural networks lead into we're not a deep learning class. There's a separate class for that, but we are definitely going to be approaching and bumping up against deep learning topics in this course, which is pretty cool. Okay. So that's all I have for this week, for Tuesday, and then I'll get these uploaded. And if you've got any questions about any of the topics we've covered today, feel free to reach out or email, and then I will see everyone in our next class. All right, take care, everyone.